with the relations. We're going to start with the relations. Okay, so by the end of this unit, you should be able to describe the concepts of relations between two sets, use the appropriate methods for representing relations, explain some of the properties of relations. So that's what you are required to know for this module. So at first, I'm just going to start with the definition of a relation. What is a relation? So let X and Y be two sets, and a binary relation or a relation R from X to Y is a subset of the Cartesian product of X cross Y. If X, Y is an element of R, or if X, Y is in our relation. So I just need to pick a highlighter. So I'm just saying, if this X and Y are in a relation that you are saying, we write X, then R, Y, which means X is related to Y. I'm sure you have done the Cartesian product. This thing that we call Cartesian product, I'm sure it's not new. On our previous lecture, when we were talking about sets, yes, there was a Cartesian product of sets where we say set A cross set B. So that cross product, we are going to come up with a subsets with some sets, right? With some sets. So you are saying a relation R from X to Y is a subset of the Cartesian product. So whenever you do the Cartesian product, you come up with this with a list of sets. So a relation is something which is a subset of that Cartesian product. So we are taking a relation from the Cartesian product. I'm sure you do remember on how you can come up with a cross product, and you are not required to do the Cartesian product so that you can come up with a relation. No, but I'm just saying so that you get the basic of what a relation is. It's just a subset of a Cartesian product. So if you're given two sets, X and Y, a relation from those sets is just a subset of a Cartesian product of those sets. I'm sure we are clear, and you can write it as what? As X, R, Y.
We are not seeing what we are sharing. We are sharing something.
I'm sharing I'm sharing a slide. I don't know if it is the same with others.
On my side, I'm not seeing anything.
Yeah, I can see.
On your side, you can see. Okay,
Yeah,
so
I can see.
On my side, I'm seeing it.
okay, so I think it's yours. Is it Nikazino?
Yes, sir.
Okay, maybe you can try to log out and rejoin. I'm sure it's your network. It's on your side. I think it will be a quick fix on that one. Okay, thank you for that. Then on the second definition, we are saying the set X is an element of X such that XY is an element of R, or XY, this one is part of our relation for some Y is element of Y, is called the domain of R. We are talking of the domain of R. The domain are the values of X, that's the domain, and then the range are the values of what? Are the values of Y. That's the range, just like that. So there's a domain for a relation, then there's a range. The domain are the values of what? Of R, and then the range are the values of Y, just like that. And then this is just an example. If X is a set of students, X, which is a set of Jim, Shayla, Shami, Surai. I don't know, there's someone who is not muted. Do you want to say something, or Joseph? And Rumbidzai, maybe? Okay. And Rumbidzai, may you please mute yourself? Rumbidzai, I'm sure
Okay,
Rumbidzai together.
checking where to mute.
Or let me help you. I muted you. Just leave it like that, unless you want to contribute. Guys, let's make sure that we mute ourselves as well as switching off our cameras. Thank you for that. Otherwise, you keep on disturbing me. Okay, So I was saying, let's say we have got a set of students which is called X, and it have got Jimmy, Shayla, Shami, and Surai, and Y is a set of courses like computer science, maths, art, history. So a relation R between X and Y, indicating courses taken by students, can be written as this Jimmy is taking computer science, Shayla is taking maths, Jimmy is taking art, Shami is taking history, Shami is taking computer science, Ray is taking maths, something like this. That's what you call a relation. And if you look at this, relation, we are saying this is a subset of a Cartesian product. Like if you asked you to find the Cartesian product of a set X, f a set xy, you is just going to cross maybe Jim and this and this and this, maybe Jim and his up to history. Then you go for Sheila with computer science, maths, art, and then history, Shami with everything, Surah with everything. So you take the subset of that as your relation according to your definition, a relation record, which is which per relation. Because not got a relation, I want it to be a relation of this and this and this. That's how you get your relation. So since Shami, then history is an element of our relation R, we may write Shami related to history, just like this. Shami, then R history. It means Shami is related to history. So we can represent a relation in above example pictorially by using an arrow diagram as follows. So you can use a diagram to represent a what? To represent a relation. So you can do it by having the first set and the second set, and then you can use these small arrows. And then don't confuse it with the arrow diagram. I'm just going to show you the arrow diagram where you're asked to draw an arrow diagram. It's not like this. Okay. Then suppose that this one is an example 2. Suppose x is equals to 2, 3, 4, and y is equals to 3, 4, 5, 6, 7. If we define a relation R from x to y by x, y is an element of R, if x divides y with the 0 remainder, we obtain R as this one. We are saying after doing the cross products of x to y, we just want a subset, which is our relation. And then we are saying this relation is such that if x divides y without leaving a remainder, so this is our values for x, our domain. These are the values for y, our range. So the relation will be just like this: 2, 4. Why do we have this 2, 4? We are taking this 2 and this 4. Why are we taking that? Because we say that x must divide y. So this is our x2 can get into what? Can get into 4. So I just want to add people, or I just want to log in on. Okay. So I'm just saying here, we are having, that's why I want people to join earlier. That's why I want people to join early. Okay, so here I've got 2, 6. Why are we having this 2 and 6? It's because this 2 can get into 6, 3 can get into 3. This 3 can get into 6, this 4 can get into 4. So all these values are for x. This 2 is for x, this 2 is for x, this 3 is from x, this 3 is from x, and this one is from x. If you look at this 4 is from what? Is from y. This 4 is from y, this 6 is from y, this 3 is from y, this 6 is from y, and this 4 as well is from what? Is from y. So we are just taking the values from x as the domain, and then the values from y as the range. So you are just looking at the condition. Does this x divides into a certain value in y? If it does, then we need to pair them and just put them as a subset in our relation, because it satisfies the what? The condition. That's how we come up with these relations. So there is a rule which is mapping, and then you just take that. Okay, so the domain of R is the set 2, 3, 4, and the range of R is the set 3, 4, 6. So this relation can be represented pictorially as follows. So here we are saying true. If you look at true, may you please make sure that you are muted. You are on mute. It's Cherit. Let's make sure that you are on mute. Sure, these are the people who are just joining now. Okay, so here I'm just saying these two, if you look at these two from our domain, is mapped 2 with a 4. That's why you've got an arrow from 2 to 4, and then 2 to 6. That's why you've got an arrow from 2 to 6. So just the same with a 3. You look at 3 in the domain. This is the domain part, and then this is the Y part, which is the range. So if you look at 3, is mapped to a 3 as well as mapped to a what? Cherit. Ungaona uzoburitsa muno musazoti takashata anditi. Let's try to respect the ground rules. Let's try to respect the ground rules. If I say mute your mic, I mean it. Okay. So this one was just an exercise. We say suppose that you've got an X and Y. This is the set with the 1, 2, 3, 4, and 5, and Y. You've got 3, 6, 9 as elements. You are asked to write a relation R between set X and set Y, which is defined by that X, Y is an element of a relation if X is less than Y. So you have to look, whenever you have the X which is less than Y, you take that set and then put it in your relation. So like here, 1, 3 will be part of that set, will be part of that relation. 1 and 6 will be part of that relation because 1 is less than this 6, and then 1 and 9 as well. 2 and 3, 2 and 6, 2 and 9, 3 and 3, it's a no because 3 is not less than 3. And then 3 and 6, yes, and then 3 and 9, yes. 4 and 3, it's a no because 4 is not less than it's not less than 3, just like that. Then on this one, you are asked to have a relation where your Y is always equal to 2X. So your Y is this one. The value of Y must be always equal to 2X for it to be in that. So if you look at that, if you take your X as 1, do you have your Y when it's equals to 2 times 1? No. If you take it as a 2, do you have your Y as a 4? No. If you take 3, do you have your Y as 6? Yes, so 3 and 6 will be part of that. But if you take a 4 here, there's no 8. If you take a 5, there's no 10. So that relation is going to have 3 and 6 only, 3, 6 only. So that's how you formulate some relations. So you can have a relation on a single set, like a relation on a set X. What you need is just to have a cross product of these two, or you just need to use this set as set X and then use it again as set Y. So all the values will be from the one set. Okay. Then let's talk of an inverse of a relation. So let R be a relation from X to Y. The inverse of relation R denoted by R to the power -1 is the relation from Y to X. It's the relation from what? From Y to X. So instead of a relation from X to Y, it's now going backwards from Y to what? From Y to X. So the inverse of a relation R is YX is such that XY is an element of R. So we are just saying whenever you have an XY as an element of R, if it is the inverse, now the range will become the domain will become the range, just like that. So you just interchange the values. So if we define a relation R from X to Y, like we have this sets X and what and Y, and then if we define a relation from X to Y by XY is an element of R. If X divides Y, we obtain this. I'm sure you've done this example. After having this, if you want the inverse of this relation, so this is the relation that we have on this picture, the pictorial diagram. such that 2 is mapped to 4 and 2 is mapped to 6. That's why you have these arrows from 2 going to 4 and 2 going to what? Going to 6. It's just the same 3 to 3 and then 3 to 6. Because we've got this 3 to 3 and 3 to 6, just like that. So if you want the inverse of this, it's now from this direction going this direction. So this is just the example of the inverse of that relation. Instead of having, maybe let's say instead of having a 3 to 3 and then a 3 to 6, what you have now, if you look at it, this one 3 to 3, but this is now a y, and then again this 6 is going to what? This 6 is going to 3. So this is now the y going to what? Going to x. But we are just reversing. So this 3 3, and then you are going to have a 3 6 instead of 6 3. We're going to have a what? Sorry, when we're having a 3 6, we're going to have a what? A 6 3. When we're having a 2 4, we're going to have a 4 2, just like this. When we're having a 2 6, we're going to have a 6 2, just like this. So that's the inverse of a relation. Then let's talk of the composition of relations, the compositions of relations. Now we are saying we have more than 2 sets that we want to combine. So how do you do that on a relation? You want to find a relation given 3 sets. So let R1 be a relation from X to Y and R2 be a relation from Y to Z. So the composition of R1 and R2 denoted by R of R1 is the relation from X to Z. So you are saying we've got 2 relations, the one from X to Y and then the one from Y to Z. So we've got the X to Y and then the Y to Z. The composition of those 2 relations, it will be something like we will be now wanting to connect X to Z. We'll be now connecting X to Z, but we'll be connecting X to Z through what? Through Y, just like that. So we are saying xz such that xy is an element of R1 and yz is an element of R2 for some y is an element of y. So we are saying we've got this relation R1 and this relation R2, where R1 is xy and then R2 is yz. So the relation that will be coming up with after the composition of relation, it will be xz. It will be xz. Because we are saying xy and then yz. So whenever I've got, so it's like you can go from x to z through y, you can go through xy, and then after y you can go to z. So whenever you have that full path xy then yz, it means that the value here at z can be derived from this x through y. So you can just directly connect x to what? X to z, something like that. That's the composition of what? Of relations. So I'm sure I've got an example. Suppose that we have 2 relations, R1 and R2. So with R1, we've got this 1, 2, 1, 6, 2, 4, 3, 4, 3, 6, and 3, 8. And then on R2, which is linking Y and Z, we've got 2U, 4S, 40, 60, and 8U. So from the definition 2, 3A, the relations can be presented pictorially as like here, if you look at 1 2, that's here 1 2, at 1 6 1 6, that's this arrow 1 6. We can go for 2 4, that's this arrow 2 4 here. You can go for 3 3 4, this is this arrow from here to this 4, and then 3 6 is from 3 to what? To 6, just like that. 3 8, it's from here to here. And then after that, we've got the R2. R2 is starting, we've got this 2U is starting from Y to Z. And then we've got this 4S, this 4 to what? To S, sorry. And then we've got this 4 to T, and then we've got 6 to T and 8 to U as well. So if you want the composition of these relations, like R1 of R2, what you need to do now is to jump from X to Z. So we can go from X to Z through these 2. So we can have 1U as the result of this composition. Just 1U can also have 2S, can also have 3S, from 3 to 4 to S there. You can also have 3T, just like that. Also you can have, yeah, this 3T again. So you can have this 3U from 3 then through 8 to this one. So you can have 3U. So we are just saying if X, Y is related and Y, Z is related, so be it for X, Z, they are also related. X anokama na Y, Y anokama na Z. So X anokama na Z, just like that. That's the, so this will be the results that we come up with after the composition of these two relations. We're going to have 1U. This 1U is coming from this through to 1, 2, then to U. So we have this 1U, and then we have this 1T as well. 1T is, I'm sure it's through 6 and then to T. I'm sure you are getting the picture of it on how are we arriving on this binary sets. We are calling binary sets because this one, it's a binary thing. We've got this value and this value, two values, so it's a binary set. It's just a binary set. Trying to add people who are in lobbying. Okay, so that's the composition of two relations. That's the composition of two relations. So before I dive into these special types of relations, do we have examples on the introductions of relations? What are relations? And some examples that we have covered on relations, as well as the composition of relations. Do we have examples before we look on these special types of relations? Or contributions? Do I have questions or contributions? Okay, so let me try to move faster. So there is a relation on a set. So those relations that we're doing is a relation from set X to set Y, or from one set to another set. So we've got some relations on a set. Okay, so we've got these types of relations on a set: reflexive relation, symmetric relation, antisymmetric relation, transitive relation. So your job is just to understand what is a reflexive relation, how does it look like, maybe to know the properties of it or the characteristics of it. So just like that, from reflexive to symmetric to antisymmetric and transitive relation. So relation on a set. So a binary relation R on a set X is a relation from set X to a set X. So it's a relation from a set to itself. So for example, let R be a relation on X, which is 1, 2, 3, 4, 5, defined by XY is an element of R. If X is less than or equal to Y, XY is an element of X. So we are just saying if X is less than or equal to Y, then XY can be the element of, where XY is an element of X. So we are just saying X and Y, they are both from the set X, because we are using the same set. So then R, or the relation R, will be a relation with these values, these all values. We are just looking at the value must be of X must be less than or equal to Y. So 1 will be less than or equal to 1. So that's why we have this. Also 1 will be less than or equal to 2. That's why we have this. 1 will be less than or equal to 3. 1 will be less than or equal to 4. 1 will be less than or equal to 5. That's why we have all these values. So you can go on to 2. 2 is not less than or equal to 1. So you cannot have 2, 1. Then 2, 2, because 2 is less than or equal to 2. Then 2, 3, because 2 is less than or equal to 3. Then 2, 4, and 2, 5. That's why you have all these values. You can do the same with a 3. 3 cannot be paired with 1, because 3, 1, 3 is not less than or equal to 1, which same applies to 2. And then 3, 3, yes, because 3 is less than or equal to 3. And then you can have a 3, 4, and a 3, 5 as well. That's why you have all these values. You can do the same on a 4. 4 cannot pair with all these values, because 4 is always greater than these values. So you can start from 4, 4, and then you have a 4, 5. And then if you go to 5, 5 cannot be paired with all these values, because 5 is always greater than or equal to all those values. So we only have a 5, 5. So this will be your relation. That's how you formulate a relation from a given set. So the domain and the range of R are both equal to what? Are both equal to set X. I'm sure we agree on this one. Okay, so this one was another definition, but okay, so this one is the definition of a reflexive relation. Now let's talk about the reflexive relation. So a relation R on a set X is called reflexive if X is an element of R for every X is an element of X. We are just saying whenever we have a binary relation with all the possible values in X being paired to itself, then that relation is of type reflexive. So in other words, a relation R on a set A is called reflexive if AA is an element of R for every element A in what? In A, just like that, just a simple start. So example one, the relation R on X is equals to 1, 2, 3, 4 for the example as shown in previous slide above is reflexive for each element. X is an element of X and the XX is an element of R. So we have 1, 2, 3, 4 as our elements. So if you look at this example, we have 1, 1 as part of this relation. We have 2, 2 here as part of this relation. We've got 3, 3, and 4, 4 again, and 5, 5. So whenever you have every value in X paired to itself in your relation, then that relation is a what? Is a reflexive relation. Whether we have other binary sets within that relation, the condition is that we just want 1 to be paired to itself, 1 to 2 to be paired to itself, 3 to be paired to itself, 4 to be paired to itself, 5 to be paired to itself, and then we can have any other sets there. But once those sets are in that relation is a what? Is a reflexive relation. So that's what you just want to see. If the relation is a what? Is a reflexive relation. It's just a simple start. So this one is just an example that we have. Sure, we have an example here, which is an example 2, which says consider the following relations on set this 1, 2, 3, 4. So we have got this relation R1. Can we say R1 is a reflexive relation? Can we say R1 is a reflexive relation? Sure, the answers are there, but I just want to see if we are together. Where if someone want to contribute here, is R1 a reflexive relation?
I think yes, sir.
Why?
We have a 1, 1 there. It's
Yes.
paired to itself. We were saying
Yes.
a reflexive relation. We should have those elements that are paired to themselves. So there we have a 1, 1. It's paired to itself. We have a 2, 2. It's paired to itself. We have a 4, 4. It's paired to itself. I don't know if I'm getting you right.
But are you saying we do not have a 3, 3?
All right. I now get it.
Reflexive relation.
Also, all the pairs should be paired to themselves.
Yes.
Yes, because we don't have a 3, 3 there.
Thank you. I didn't get it. I now get it. Thank you.
Okay, so that's it. This one is not a reflexive relation because we do not it's not a reflexive relation because we do not have a 3, 3. So every value in our set must be mapped to itself for it to be a reflexive relation. So if you look at this one, also R2 is not a reflexive relation. Let's look at R3. We've got a 1, 1, we've got a 2, 2, a 3, 3, and a 4, 4. So this one is now a reflexive relation. So we can safely say R3 is a reflexive relation. So on reflexive relations, you are just looking at all the elements that we have. Are they paired to themselves in that relation? So if you look at R4, it's not a reflexive relation at all because do not have these elements paired to themselves. And then R5, is it a reflexive relation? A 1, 1 yes, a 2, 2 yes, a 3, 3 yes, and a 4, 4 yes. So this R5 is a reflexive relation, but R6 is not a reflexive relation as well. So do you have some questions on a reflexive relation? I think can proceed to other relations. So now let's talk of symmetric relation, a symmetric relation. So a relation R on a set X is called symmetric if for all X, Y as element of X. If XY is an element of R, then YX is an element of R. So you are just saying whenever you have a XY, you must also have a YX for it to be a symmetric relation. So if you have a 2, 3, you must have a 3, 2 in that relation for it to be what? A symmetric relation, for it to be a symmetric relation. So there's a remark here. R is not symmetric if and only if there are elements A and B in A, such that AB is an element of R, but BA is not an element of R. So whenever you see an AB and you do not see a BA, so that relation is not a symmetric relation. Whenever you see an AB, you must see a BA, just like that. So for example, consider the relation R on X, which is A, B, C, D as elements given as follows: A, D, B, C, C, B, and D, A. Can you say the relation is symmetric? Yes. Why? If we look at this, we've got AD, right? We've got an AD. Do we have a DA? Yes, we have a DA. Whenever you've got a BC, we have a CB, just like that. So you are saying whenever you have an XY, you must also have a YX for it to be a symmetric relation. So we can go back to our example again and then point out which ones are reflexive, asymmetric relations, which ones are symmetric relations here. So this is just an example. Let A be equal to 1, 2, 3, 4, and define relations R1, R2, and R3 and R4 on A as follows. R1, we've got 1, 1, 1, 3, 2, 2, 2, 4, 3, 1, 4, 2. We've got 1, 1, 2, 2, 3, 3, 4, 4. So guys, can we pick the symmetric relation, those which are symmetric relation and those which are not a symmetric relation? Do we have someone who can contribute?
Yes,
There's
sir.
a
Yes, sir.
okay, there's a hand by Monica.
Yes, sir. I think R1 is a symmetric relation because we have 1, 3, and we also have a 3, 1. We've got a 2, 4, and we also have a 4, 2. I think it's a symmetric relation.
Okay, nice. Yeah. That's true. R1 is a symmetric relation because we have got a 1, 3, and we've got a 3, 1 as well in that relation. And we've got a 2, 4, and then we've got a 4, 2 as well. And then whenever I've got this element paired to itself, it's as good as like we've got two sets like 1, 1 and a 1, 1. So this one is always accepted in a symmetric relation. This one is paired to this one, so we also have a 1 paired to itself, just like that. What about R2? Is R2 a symmetric relation? There is a hand by Pamela.
I think 2 is a symmetric relation because it has 1, 1, 2, 2, and 3, 3, and 4, 4. I mean,
No.
Okay.
Mhm.
Monica, do you want to say something?
No, sir. I see where I went wrong.
Okay. So R2 is a symmetric relation. Why? Because we have got this 1, 1, 2, 2, 3, 3, 4, 4. So whenever you've got this 1, 1, it's as good as we have got AB and BA at the same time. Because this one is paired to 1 is just as good as 1 is paired to 1 as well. So it's a symmetric relation because we've got 1, 1, 2, 2, 3, 3, and 4, 4. So whenever you've got a 1, 1, we also have a 1, 1. Whenever you've got a 2, 2, you also have a 2, 2, just like that, because they are paired to themselves. So it's a what? It's a symmetric relation. What about R3? What about R3? There's a hand. Is it your hand, Pamela? Okay, there's a hand by Colin. Can come, you can contribute. Yes.
On R2,
Yes.
doesn't that relation has two properties? The properties are for reflective and also symmetric.
Yes, you are correct. So it can be both. A relation can be both a symmetric or a reflexive relation. It's only that now we are focusing on a symmetric relation, but it is also a what? it is also a reflexive relation. Thank you for that contribution. Okay, what about on R4? I'm sure R3 is not a reflexive relation. We've got 2, 3, but there's no a 3, 2.
R3. Oh,
What about on R4? There's Caleb. Caleb, you can contribute. I'm sure I want to say something.
Okay, I wanted to answer R3, but on
Okay.
R2, I think I can answer also. We have a 1, 1, 2, 2, 3, 3, and 4, 3, and all right. So we don't have another 3, 4 there. So I think it's not a symmetric relation.
Yeah, that's correct. That's correct. That's correct. Okay, so that's all on symmetric relations. You can always reference back here if we have some challenges on it. So let's now talk about the antisymmetric. Let's talk about the antisymmetric relation. Whenever you have got a symmetric and antisymmetric, people think that maybe the antisymmetric is the opposite of symmetric. No, no, no. Do not take it that way. Otherwise, you get lost. Antisymmetric is just a relation on its own. It's not like the opposite of symmetric relations, but there's something which we can use to define, which is like in common, but they cannot be the opposite of each other. We can safely say they cannot be always the opposite of each other. So a relation R on a set X is called antisymmetric if for all X, Y is an element of X, when X, Y is an element of our relation R, and X is not equal to Y, and XY is not an element of R. Let me try to make it simple to you. R is not antisymmetric if and only if there are elements A and B in A such that AB is an element of R, BA is an element of R, but A is not equal to B. Whenever you have AB and BA, where these values are not equal, which means that relation is not antisymmetric. So to have A, B, and BA is only acceptable when A and B is what? Is equal. That's what we call the antisymmetric relation. So the properties of being symmetric and being antisymmetric are not negative of each other. So R is antisymmetric if and only if, that's IFF mean, is if and only if A is related to B, AB, and B is related to A, only when A is equal to B. Only when A is equal to B. That's where we can have an antisymmetric relation. So for example, consider the relation R on X, A, B, C, D, which given as below, A, B, B, C, and C, D. So the relation the relation is antisymmetric because for all X, Y, when X, Y is an element of R, and X is not equal to Y, also YX is not an element of R. Like you have got AB, but we do not have a BA. Here you've got a BC, here you've got a CD. So this one can be taken as what? As an antisymmetric relation. Let's do more examples here. So let's talk about, let A be equal to 1, 2, 3, 4, and define the following relations on A. R1 is equals to 1, 1, 2, 2, 3, 3. Is R1 an antisymmetric relation? Yes. Why? Whenever we have got A, B, and BA in our relation, those values are equal. Those values are equal. Look at this one. We say R is an antisymmetric relation if and only if A is related to B and B is related to A only when A is equal to B. So here you've got 1, 1. And if you look at it, A is equal to B. Here you've got a 2, 2, A is equal to B. And here you've got a 3, 3, A is equal to B. Then if you look at R2, is it R2 in an antisymmetric relation? Is it R2 in an antisymmetric relation? To those who want to contribute. Just want to see if I've got someone who've actually got it correct. Yes, Monica, you can contribute.
I think R2 is not antisymmetric because 1 to they are not equal. X is not equal to Y. Then 2, 3, X is not equal to Y. 3, 4, the same applies as 4, 1. So I think it's not in antisymmetric relation.
And then you are wrong. I'm sorry to say, but you are wrong. You are wrong on that one. What about others? You are wrong on that one. Okay, let me just try to clarify here. What I'm saying is, whenever you have a 1, 2, you must not have a 2, 1. If you look at this, we are saying whenever you have AB and BA and A is not equal to B, that relation is not going to be an antisymmetric. But it is going to be an antisymmetric whenever A is equal to B. So we are just saying whenever you have a 1, 2, you must not have a 2, 1 in here. And we do not have a 2, 1. Here we have a 2, 2. So this one we accept because 2, 2 is as good as we have got 2, 2, and this 2 is from what? Can be from X, and then this one can be also from what? From Y. And then it's like we can have 2, 2 again, where Y is now the 2, and then X is what? Is the 2, something like that. So we are just saying this one is acceptable on an antisymmetric relation. 2, 3 is only acceptable if we do not have a 3, 2. 3, 4 is acceptable if we do not have a 4, 3. And 4, 1 is acceptable if we do not have a 4, 1. And this one passes the test of an antisymmetric relation. But if you look at it, it is also not a symmetric relation, because on a symmetric, we are saying whenever you have a 2, 3, you must have a 3, 2. Whenever you've got a 3, 4, you must have a 4, 3. Something like that. So here we are just saying we only accept it to be antisymmetric whenever we have those sets with the 2 different values. You must not have them again on the opposite way. So whenever you have a 1, 2, you must not have a 2, 1, because 2 and 1 are not equal. So it is only acceptable whenever you have A equal to B. So if you have an AB and a BA, whenever A is equal to B, you can accept it as an antisymmetric relation. So I don't know if you get it. Maybe I want to see if there are some people who are getting this correct. Is the R3 as an antisymmetric relation? Is R3 an antisymmetric relation? Do you have someone who want to explain this? Want to try this? It's good to try. It's good to try. Yes, Caleb. Yes, you can unmute yourself. You can contribute. You can unmute yourself and contribute.
Okay, I had forgotten to unmute. Thank you, sir. I think not a anti-symmetric relation, because I have seen this. We have a 1, 3 and a 3, 1 already. So it's disqualified already, because if I heard you well, you said in an anti-symmetric relation, we should not have these like elements in the opposite way. That is 3, 1, 1, 3 and 3, 1. So what I can see here already, we are having a 1, 3 and a 3, 1.
Exactly. And if you look at that, R3 is the asymmetric relation. R3 is asymmetric, but it's not antisymmetric. Okay. So in other words, if you look at R1 was both antisymmetric and symmetric. I'm just trying to clarify on this point, which says the properties of being symmetric and being antisymmetric are not negative of each other. Like it's not the opposite way. R1 was both antisymmetric and symmetric at the same time. This R1. But for R2 is antisymmetric but not symmetric, and R3 is not antisymmetric, but it is also symmetric. What about on R4? On R4, do you have someone to attempt this one on R4? Someone to contribute? Caleb again, just wait a little bit. I'm sure I'm going to get someone. Monica, just wait a little bit. I'm sure I'm going to get someone. Or I'm just going to call the names. Let's raise our hands. Yes, Tarisai can contribute. The answers are there. You can unmute yourself. Okay.
Okay. Yeah, I think we've got the same scenario here. 1, 3 and 3, 1 are existing in our relationship. So I think we could use something.
Exactly. That's correct. Thank you. So let's move on to the transitive relation. Let's move on to the transitive relation, which is mostly involve three sets. So a relation R on a set X is called transitive if for all X, Y, Z is an element of X, when X, Y, and Y, Z are elements of R, then X, Z is an element of R. But just if X is related to Y and Y is related to Z, so this X is also related to Z, just like the composition of relations. If X is related to Y and then Y is related to Z, it means that X is related to Z through this Y, So, for example, just want to accept someone who's in the lobby, okay? So, consider the relation R on X, A, B, C, D, which is given as follows: R, A, B, A, D, A, C, B, C, B, D, and C, D. So the relation R is a transitive because O X Y Z, where X, Y, and Y, Z is an element of R, there is X, Z is an element of R. For example, there is A, B is an element of R, B C is an element of R, and then we have AC. So it's just like whenever you have A, B, if you encounter B something, you must have also A something. Like you have got AB, if you look at this, we've got this BC, so we must also have an AC. We've got AB and we've got this BC, so this A must be also related to C through this B, and we have got this AC, just like that. And then we have got AD, then we now have to look for D something. If we have got D something, we must also have A something. So we do not have D something, so we cannot say so that one is just as good as that. If we don't have a D something, so it's good as that. We've got a what else? AC, to have something that I've missed on this one, and AC, and then we've got AB and then BD. Okay, we've got AC. What else? AC, do we have, okay, we've got AC and we've got this CD. So we must also have AD, yes, which is correct. We've got AB and BD, so we must also have AD, yes, correct again. So which means this one, it's a what? It's a transitive relation. It's a transitive relation. So let's look at what. Do we have more examples? No, we do not have more examples. We only have one example. I'm sorry on this one. I've just put one example. Yes. But can we have somewhere we can pick this one? Transitive relation. Can we have somewhere where we can pick this one? Where we can say this one is transitive relation. Okay, let's see if we can have a transitive relation. We've got a 1, 1, a 1, 3, we've got a 1, 3, and a 3, 1. We must have a what? A 1, 1. No, 1, 3, and then a 3, 1. Then we must have a 1, 1. Yes, we've got a 2, 4. So this one is a transitive relation. Because whenever we have a 1, 3, here we are having a 3, 1. So we must have also a 1, 1. So R1 is a transitive relation there. Why? Because whenever we've got, no, it's not a transitive relation. We've got a 2, 4, right? And a 4, 2. So we must have a 2, 2. So this one is not a transitive relation. It's not a transitive relation. We have a 1, 1, a 2, 2, a 3, 3, a 4, 2. This one can qualify to be a transitive relation. Yes, there's nothing which is violating that. Because we have a 1, 1, we have a 2, 2, 3, 3, 4, 4, but we do not have something. This one, there's nothing actually violating that. If a 2, 2, 2, 3, 3, 4, there's nothing violating the transitive relation. This one is not a transitive relation. We've got a 2, 3, and a 3, 4. So we must have a 2, 4. 2, 3, 3, 4. So we must have a 2, 4. to make it a transitive relation. So whenever having something like 2, 3, and you have 3 something, which means that something must be also related to these 2. So if a 2, 3 and a 3, 4, so these 2 must be related to 4, but it's not part of this one. So this one is not a transitive relation. If you look at this one as well, we've got a 4, 3, a 4, 4, then this one, nothing values the transitive relation here. We've got a 3, 3, but there's no 3 something. We've got a 4, 3, and there's no a 3 something. So we've got a 4, 3, right? And we've got a 3, 3. So we must also have a 3, 4. This was not a transitive relation. Yeah. This one's not a transitive relation. So sorry that I didn't add more examples on transitive relation, but I don't know if you are getting it. Are we getting it? On the definition of a transitive relation? Are we getting it?
Yes, we're getting it a bit, but we wish we had more examples.
Yeah, I'm sure something happened there. I don't know, maybe it's in there, but maybe the examples were displaced. I don't know what happened, but I'm sure it was supposed to be there. I'm sure it was supposed to be there. Anyway, okay. Let me just continue with what I have. Let's talk about a diagraph. Let's talk about a diagraph. There's what we call a diagraph, which is just the representation of a relation. So one way to picture a relation on a set is to draw its diagraph. So a directed graph or a diagraph consists of 2 finite sets. All right, it consists of what? Of 2 finite sets, a set of VG, which is a set of vertices, and a set of directed edges, which is G of G, which is directed edges. So where each edge is associated with an ordered pair of vertices called its endpoints. So it's just like from node 1 to another node, from node to another node. Those are the edges, and then the vertices are the nodes. So if edge is if edge E is associated with the pair VW of vertices, then E is said to be the directed edge from V to what? From V to W. Just like that, from V to what? To W, and is represented by drawing an what? An arrow from V to W. So this one is just an example of a diagraph. So we have got a V3 and a V2. So this one is just an edge. So if there is no direction, it means that this one is just bidirectional. You can go from V3 to V2 and V2 from what? From V3. And then we've got this one, which is going from V3 to V4 as well as V4 to V3. This one is just an arrow, which means there is an edge which is going from V3 to this V1 as well as from V1 to V3. So this E3, there's an arrow, there's a direction. So V1 to V3, and then E2 is from V3 to V1. And then there's a loop. This one, we draw a loop whenever we have got a V1 here. So this E1 is just a loop. It means we've got the vertex, which is actually mapping to itself. That's why we've got this loop. So you represent it by a loop. Whenever you have got something like this, 1, 1, you draw a loop on what? On 1, 1. So if you're going to have a diagraph for this R1, it means you're going to have 1 as a vertex, 2 again as a vertex, and then 3 again as a vertex. And then what you do on here on 1, we've got a 1, 1. So you put a what? You put a self loop there. And then on 2, 2, you put also a what? A self loop. And then on 3, 3, you also put a what? A self loop, just like that. Then this one will become a diagraph for this relation. If you look at this one, this relation, you have to put maybe, let me just wrap everything here. Okay, let me just wrap maybe everything. Okay, let me pick my highlight. I have a lot of people who are requesting to join. I hope they will mute themselves as soon as they join. Okay, Sure, they mute themselves, I'm sure. Okay, thank you. So I was trying to draw this one, right? So what you need to put first is the vertices 1, maybe 2, maybe 3, and what? Maybe and a 4. I just put the numbers randomly, but you need to be strategic with the sets that you have here, with the sets that you have here. So we've got a 1, 3. So there's a vertex there's an edge from 1 to 3. So from 1 to 3, right? So you put the direction just because 1 is at the start and 3 is at the end. So it's from 1 to 3. Then we've got a 2, 4. So from 2 to 4, right? From 2 to 4. And then we've got a 3, 1. From 3 to what? To 1 again. So just like that. And then from 4 to 3. From 4 to 3. So this one will be a diagraph for this relation. This one will be a diagraph for this relation. Just like that. So that's how you draw a diagraph, and that's how a diagraph look like. Do we have questions or contributions on diagraph? We have some questions here. Okay. So maybe if you do not have questions, I was looking forward to hear some of the questions, but maybe if I dive into that, that's where the questions are going to come in here. Okay, but anyway, let's look at the characteristics of a relation and a diagraph. Sometimes you'll be asked to say if a given relation is a reflexive relation by just looking at its diagraph. So you'll be given a diagraph of a relation and asked to say, is it a symmetric relation? Is it a reflexive relation? Is it an antisymmetric relation or a transitive relation? So for you to be able to do that, you need to know these properties or these characteristics. So a diagraph for a reflexive relation has a loop at every vertex. So if you look at the diagraph that I've actually first draw for this relation, you see that we have got a self loop at each and every vertex, which means that relation, if you look at that diagraph, you can pick that it is a what? It is a reflexive relation, just like that. Then for a symmetric relation, is the property that whenever there is a direct edge from V to W, there's also a direct edge from W to V. So there will be always an arrow going the reverse one. Just like here, maybe for a symmetric relation, if I'm just trying to, okay. I just want the highlight. I just want to erase something. This is the symmetric relation. Okay. Just want to erase and I just want to draw a symbol. One here. Which one was a symmetric relation? A symmetric relation. Okay, R2. Where is R2? This one. Okay. No, I do not want that one. Is R1 is symmetric? Yes. So I just want this one. I've got A1. And I've got a 2, I've got a 3, maybe, and a 4. Okay, so here I've got a 1, 1, which is a self loop. I've got a 1, 3 from 1 to what? To 3. And then we've got a 2, 4 from 2 to 4. And I've got a 3, 1 from 3 to 1. Then I've got a 4, 2 from 4 to what? From 4 to 2. Right? And then we are saying for a relation, on a diagram, for you to pick if the relation is a symmetric relation, is the problem that whenever there is a directed edge from V to W, there is also a directed edge from W to V. So whenever you have a directed edge from V to W, so from 1 to 3, we must also have a directed edge from 3 to what? From 3 to 1. Whenever, sorry, this is not the diagram that I'm supposed to use, so right? Like here, whenever you have a directed edge from 1 to 3, you must also have a 3 to 1. From 2 to 4, you must also have a 4 to 2, just like that. And then it's a self loop, so it's as good as from 1 to 1 and from 1 to 1. So it's a what? This one is a symmetric relation by looking at this diagraph. So you will be not given the numbers, you'll be given the diagraph, and then you'll be given both the numbers and the diagraph, and be used, and you'll be you can be given the numbers and then asked to draw the diagraph, and then you'll be asked to say if it is a reflexive relation or not, or to be asked to classify that diagraph into those symmetric, anti-symmetric, reflexive relation as well as transitive relation. And then you could classify by giving the supportive characteristics of that diagraph, so that you can classify it, just something like that. So those are some of the questions that you'll be asked. And then on an antisymmetric is the property that between any two vectors there is at most one directed edge. And then you are saying is the property that between any two vertices, there is at most one directed edge. On transitive relation is the property that whenever there are directed edges from X to Y and from Y to Z, there is also a directed edge from X to Z. So as just saying X to Y and then Y to Z, we must also see X jumping straight to Z, just like that, for it to be a transitive relation. Do I have some questions here? Do I have some questions here before I move on to the next slide? Do I have some questions here? Okay, so I think I'm now having our 1 hour lapsed. Okay, let's talk about the partial order. Here I'm not going to take much of your time because we've done all the relations on a set. Maybe now what we just want to understand. Yes.
I want to ask on reflexive, what do we call a loop?
A loop is whenever you have a vertex which is mapping to itself, like a 1-1. You call it a loop because you'll be having an arrow which will be starting at 1 and ending at 1. So it's just a loop from 1 to 1. We are just having an arrow which is going straight from 1 and going back to 1.
Okay, I've understood. Thank you.
Okay, there is a hand at Colin Mshamba. You want to say
okay,
something?
so I wanted to ask, yes, I wanted to ask on the properties of a diagraph. When you were explaining about the transitive being reflective, both reflective and symmetric on those other relations, which means on the diagraph you can't prove that. Am I right to say that? Because from the explanation of the diagraph, you only have self-looping on reflective relations, and on symmetric you don't have self-looping at all. You only have directed vertices.
Okay, maybe your question is not actually, I'm not getting it correct, but I wanted also to correct you on the issue of reflexive relation. It's a reflexive relation, not a reflective. I'm sure I have some of the students who were writing that on the previous exams. You can fail by just a mere technicalities, reflexive, not reflective. And then on the diagraph, I'm sure we can have an antisymmetric and asymmetric relation on a diagraph. And we know that a symmetric relation can also be an antisymmetric relation. So if you look at the diagraph, if you have the properties or the characteristics that shows that this one is a symmetric relation as well as an antisymmetric relation, you can just prove that it's provable. It's something that you can prove. Something that you can prove by saying the characteristics of those relations on a diagraph. How do they look like? Like if I come here, I'm saying if it is an antisymmetric, there are these properties. And then if it is a transitive, if it is a symmetric relation, there are these properties. So if it meets both of them, it means it's both symmetric and antisymmetric. But if it meets one of these two, it means it's of that type that it means. Just like that. I don't know if you are getting me correctly. Unless, I don't know. Are you answered?
Yeah, no, it's fine, but I was referring on the reflexive and symmetric one. If you go back to that other table,
On a
where we
reflexive,
have and symmetric,
on the table, which table now?
the one which has got reflexive, the one which I think was R2, which had both reflexive and symmetric symmetric elements in it.
Symmetric and asymmetric. Okay, you've got R2 also symmetric relation.
Yeah, yes, it's R2.
R2. Okay, this one.
Yes, and then if you are asked to draw a diagraph of that relation, how will it come out?
Okay, let me just draw it for you. Maybe it's good if we experiment with it. Let me just erase everything. Let me just draw it, and then you look at the properties. Okay. We are going to draw R2. We have got 1, we have A2, we have got A3, we have A4. And then you are saying R2, we've got A11, which means it's a self loop. Here it's a loop. R2, then you've got a 2, which means there is a what? There is a loop here. Then there is R3, sorry, there is a 3, which is also a loop. Then there's a 4, which is also a what? A loop. Right? And then you're asked to say which relation is this one, right? And then you're asking how you can take it, both it's a what? It's a reflexive as well as a what? As a symmetric relation. It's also a symmetric relation. So if you go to the properties and read these properties, for a symmetric relation, we are saying has the property that whenever there is a directed edge from V to W, there's also a directed edge from W to V. And then reflexive, we are saying is a loop at every vertex. So if you look at this, the diagram that we have drawn here, whenever we have an edge from 1 to 1, we also have a 1 to 1, just like that. So we have got whenever we have a 2 to 2, we also have a 2 to 2, just like that. It's a 2 from 2 to 2, and here it's from 4 to 4, and then here is from 3 to what? To 3. And also if you look at the reflexive part, we are saying whenever you have a self loop at every vertex, and we have a self loop at every vertex. So this one qualifies to be a symmetric as well as to be a what? To be a reflexive relation. I don't know if you're answered now.
Yes, I am. Thank you.
Okay. So I think it's just a matter of mastering these properties. You'll be good to go. You'll be good to go. And then let's talk about the partial order. Also, yes, just a matter of mastering what is partial order. If you know what is partial order, then you know everything according to what we have done. I'm not going to waste much of our time here. So by definition, a relation R on a set X is called partial order if R is reflexive, antisymmetric, and transitive. So if you are being asked to assert that is this relation of partial order, you just need to check if it is reflexive, antisymmetric, and transitive. And we have actually done that. So what you need to check if it is reflexive and antisymmetric and transitive at the same time, it means that relation is of partial order. So if you asked to prove that this relation is of partial order, you need to prove that it is a reflexive relation by stating the properties of a reflexive relation. And then you go on to check if it is antisymmetric and check if it is transitive. If it certifies that, then if it satisfies that, then you can say that this relation is of partial order. So here we are given this set X, and then this relation on set X with 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 2, 2, 2, 4, 3, 3, 4, 4, and 5, 5. So you first check if it is reflexive. Yes, it is reflexive. Why? We've got a 1, 1. Do we have a 2, 2? Yes. Do we have a 3, 3? Yes. Do we have a 4, 4? Yes. And a 5, 5. And then we check if it is antisymmetric. So here we are saying it is antisymmetric. Why? Whenever you have a 2, 1, 1, 2 is not part of this. Whenever you've got a 3, 1, 3, 1, 1, 3, do we have a, okay, so we are saying here we have a 1, 2, and we do not have a 2, 1. Here we've got a 1, 3, we do not have a 3, 1. We've got a 1, 4, we do not have a 4, 1. We have a 1, 5, we do not have a 5, 1. Also we have a what? 2, 4, we do not have a 4, 2. So we only have, maybe we only have 2, like from 1, 1, 1, 1, 1, 1 to 1, 1, 2, 2 to 2, 2, something like that. So this one can be an antisymmetric, if you know, you know. And then for transitive, whenever you have a 1, 2 and a 2 something, you must have a 1 something. So here you've got a 1, 2, right? Do we have a 2 something? We've got a 2, 4. So we must have a 1, 4, and it's here. Whenever you have a 1, 3, do we have a 3 something with a 3, 3? So you've got a 1, 3 and a 3, 3. So it means we've got a 1, 3 again. Yeah, so this one is still fine. What else? We have a 1, 5. Do we have a 5, a 1 something? The for transitive, we've got a 1, 2, 2, 4, and 1, 4 are in R. You can actually go on to prove that. You can just go on to prove that. Once you are able to prove that, you can say this one is of partial order. Then on the equivalence relation, a relation that is reflexive, symmetric, and transitive. So take note of these differences. Here we are looking at antisymmetric, reflexive, antisymmetric, and transitive. Here we are looking at reflexive, symmetric, and transitive. So we are only changing this one. So equivalence relation is when you have reflexive, symmetric, and transitive. So you need to check the relation that we are given. If it is reflexive, symmetric, and transitive, I'm sure you can do that. Once you have mastered what a reflexive relation, symmetric relation, and transitive relation is, you can actually assert if the relation is an equivalence relation. So do I have some questions here or some contributions? I have some questions or some contributions. Okay, so I think it shows that everyone is satisfied. So if so, that's the end of this presentation on relations. So if there are no questions on relations, it means we are good to go with the relations, and I am done with the relations. Can I say that I'm done with the relations? We are done with the relations. I'm not seeing any feedback. Okay. It looks like you've gone for a break. Caleb, you can say something.
I think you can say you have done with the relations. I think it's our duty now to go and master it and see if we can get more examples and we can master it. I think I had a question if we are going to have other tutorials on other topics, because I think, yeah, you can teach very well. I think I am grasping the concept, and others as well. I think they are.
Okay.
So
okay.
The question is, are we going to be having other tutorials before we write the exams?
Okay, this one is a long tutorial because we're not just going to cover one topic. I'm sure you are left with the 2 topics. I don't know if I can manage, but yeah, you need to do the functions, and the third one, I'm sure it's on the sequences. Yeah, and then Primrose, you want to say something? Primrose Nesta. You can contribute or you can ask.
Yes. Also, I joined the tutorial late. I just wanted to ask what else we had covered. We had covered relations only or other.
Okay. It's relations only. It's relations only.
Okay, so thank you.
Okay. And also I've shared the recording. I'm sure I'm recording. Yeah, I'm sure I'm recording. Okay, so I'm just trying to open another slide. So let me just wait for me while I'm opening the slide for functions. Yeah, we need to cover functions as well. I'm sure this one is also a very important topic for your exams. I'm sure even in your assignments, there was something on this. So I'm just going to share this window on functions. I'm sure we can quickly adapt. We're talking of relations. I'm sure we can quickly adapt to functions. Why? Because functions are also part of what? Of relations. You cannot talk of a function without a relation. So a function is just like almost a subset of a what? Of a relation. We have started from Cartesian product that we've done on the sets, and we've said a relation is a subset of a what? Of a Cartesian product, and now a function is almost like a subset of a what? Of a relation. So just like that, so I'm sure we can quickly adapt to functions. I'm sure there is no we are not going to face any challenges with the functions, and I'm also sure that some of these things, to those who have done A level, you are good enough to do this. For those who do not did A level, I'm also sure you've done some functions, some sort of functions at all levels. So it's not something which is that much big. Okay, so by the end of this unit, you should be able to describe the concept of functions, represent functions by using graphical representation, identify different types of functions. So functions, by definition, a function f from x to y is a relation from x to y having the following properties. So you are seeing this keyword. A function is also a relation. So a function f from x to y is a relation from x to y having these properties. One, the domain of f is x, right? The domain of f is what? Is x. We are saying it's a relation from x to y. So this x is the domain of our function. Two, if xy prime are element of f, then y is equal to y prime. We are saying whenever we have an xy and maybe xz, y must be equal to z. Don't know if you are getting me here. Let me just try to repeat this one. Whenever you have an xy and x something, that x something must be equal to this y. That's what I'm trying to say. So in other words, if I'm having 1 and a 2 here, right? And maybe I've got the output maybe as a 4 and a 5. So I'm saying whenever I'm having an x, maybe and 4, and an x and 5, something like this. Instead of having something like this, we are saying whenever you have 1 and a 4, and you have 1 and something else, that something must be this 4. So this one will be not a function. From this property, it's not a function. We are saying 1 and 4, and then if we have 1 and something else this side, or 1 mapped to something else, that something must be this 4. Otherwise, it's not a function. In other words, on functions, we do not have one value being mapped to many values. There is no such a thing in functions. Let me erase this. Maybe I can try to, because we do not want to have some conflicts later. So I'm saying if you have a 1 and a 2, maybe and a 4 and a 5, for it to be a function, whenever you have a 1 and a 4, we must not see 1 being mapped to any other values in the y set. This one is the domain, and then this one is the range. we must not have a single value being mapped to many values. Okay, that's the property number 2. So a function from x to y is sometimes denoted by f is such that x is mapped to what? To y, something like this. It's a notation of writing functions. So we can have something like this. This one is our x, and then this one is our y. This one is a function y. We've got this one mapped to a, and there's no any other way this one is mapped to any of these values. 2 is mapped to b. There is no 2a or 2c. So this one is still a function. 3 is mapped to a. So we can have 2 values being mapped to one value. It's still okay. But to have one value being mapped to more than one value on the y side or on the range, that one will disqualify it from being a set. So in other words, not all the relations are functions. So not all the relations are functions, but some of the relations are what? Are functions. That's what we mean here. Okay, so let's talk about the domain and range. I'm sure these are not new words or are not new it's not a new grammar to you. I'm sure you are well versed with the domain and range. So the domain of f is x and the range of f is is ab. Where is it? All right, here. This one, if we look at this one, I think it's this one. This one is our domain, and then the range is AB. Those are the values that we are having. So the range of a relation R is the set Y is an element of Y such that XY is an element of R for some X as an element of X. So the set of range or the range, those are the values of Y, which will be occurring whenever we have X mapped to Y. So whenever you are having X mapped to Y, this Y will become our range. So like here, we've got A and B as our range for this relation, for this function, for this function, just like that. So example, the relation is represented as f of x equals to x squared. This relation is a function, and the domain is the set of all real numbers. It's the domain is the set of all real numbers. So this one, if you look at this, if you put one value, you get one value. That's why this one is qualified as a function. But otherwise, if it was a square root of something, we're going to have 2 values for a single value. So that one is not a what? It's not a function. Unless if you neglect maybe the positive one and just say you want the negative values or something like that, it can now become a function. So example 2, we can apply the function given in example 1 as follows. If you are given 2, you are going to get a 4. If you are given 8, you are going to get a 64. So that one will become a what? A function on itself. Okay, so this example, we've got this example, which of the relations define functions from x 2, 4, 5 and to y 1, 2, 4, 6. All right, so you are saying all these relations, which relations are functions, which relations resembles a function. There's someone who is trying to join. We just say which relation resembles a function. Let's look at R1. Is R1 a function? You are saying R1 is not a function. Why? Because 5 is an element of X, does not appear as the first element in any ordered pair in R1. So we are saying here we've got this as our domain 2, 4, and 5. But on this one, we are not seeing this 5 as part of the domain. So in other words, R1 cannot be taken as a function from X to what? To Y. What about R2? We've got a 2, 4 and a 4, 1 and a 4, 2. Remember, this 4 is being mapped to 2 different values, 4, 1 and 4, 2, which means, in other words, we end up having this shape where you have X having a one value mapped to what? To 2 different values. So in other words, R2 is not a function. So if you want to see the given relation is a function, you can just maybe list the domain part and the the range part. If you have one value which is being mapped, or if you have this sign which will be looking like a less than, or you have maybe one value here mapped to many values, or to 2 or 3 values, 4 values, or I don't know, even to infinite numbers on the range side, it means that it's not a function. That relation is not a function. Let's look at R3. At R3, we've got a 2, 4, a 4, 1, and a 5, 6. This one is a relation. Why? This 2 is part of our domain. This 4 is part of our domain. This 5 is part of our domain. And also this 4 is part of our range. 1 is part of our range. And 6 is part of our range. And if you look at it, there's no where we have the domain or the value of x being mapped to 2 values in our range, or more than 1 value in our range, just like that. So that's how you can define a function, or that's how you can see if a relation is what is a function. Maybe now we want to look at the graphs of a function. These graphs of a function, how you can draw that. I'm sure this one is an all-level work. I'm not going to dive deep into this one. I'm just going to assume. I know my assumptions are not going to use around, but this one it's a good assumption. I'm just going to get over it. So if you want to draw a function, maybe given y is equals to f of x, what you just want to do is just maybe to define a range, and then you just the range of values of x, and then you just plug those values. You get every value of y for every value of x, and then you plot those values. Like here, if you put -3, you are given this y is equals to x squared. So if you put -3 here, you get what? -3 squared, you get a 9. Then you plot, you go for -2, you put -2 here, and then you plot, you put, and then you plot, and then you put the line which will be joining those values. And remember, this one was a quadratic equation, so it was going to give you this graph, a quadratic expression. So it was going to give you this cup shaped graph. I'm sure this one is not more challenging. It's not such challenging. So let's talk about types of functions. I'm sure here that's where you need to get it correct. Otherwise, it will confuse you forever. So you need to make sure that you listen to this one. So there are 3 types of functions, and they are injective, surjective, and bijective. We have these 3. An injective one, a surjective one, and a bijective. So you need to master which one is injective, which one is surjective. If you know that, it will become very easy to understand the bijective one. I'm sure he will agree with me later on that one. Okay, so the definition of an injective function: a function f from x to y is said to be 1-to-1 or injective if for each y is an element of y, there is at most one x is an element of x, with f of x is equal to what? Is equal to y. Normally, these are the standard definitions. So sometimes you do not get it on the way that they are written. But normally, I think here you've noticed something. An injective function can be referred to as a 1-to-1. So whenever you ask it of a 1-to-1 function, you are also being asked of an injective function. Just get it that way. Also here we are saying that the condition given in the definition above for a function to be 1-to-1 is equivalent to: if x prime is an element of x, then f of x must be equal to f of x prime. Then x is equal to x prime. So we are saying if you are given maybe something like xy as an element of our x, it means that the f of x must be equal to f of y, which means that x is equal to y, something like that. Let's just look at this one, this function, which is a 1-to-1. We are saying you must have at least this element must be mapped to one of these elements, and it must be just mapped to one of these elements. Like you've got a 1 to B, and a 2 to C, and a 3 to A. Then this one, you can safely say it's a 1-to-1 function. Why? Because all these elements in the domain, they are mapping to at least one or to at most one of these, right? At most one of these, yeah. At most one of these. So a function f from x to y is said to be one-to-one or injective if for each y is an element for y here, there is at most one x is an element of x here, with f of x is equals to y. When I say f of x is equal to y, when you put 1, you are going to get the value of y. So when you put 1 in our function, you are going to get a b, which is the value of y. And whenever you put a 2, you're going to get a c. Whenever you put a 3, you're going to get an a. So this one is a one-to-one function. It's a one-to-one function. For every value that we have here, sorry. Okay. Okay, so for every value that we have here, in our x, those values, they're actually giving us a value in our range, and it's a single value. So there is at most one x in x with f of x is equal to y, just like that. Just like that. So that's what a one-to-one function look like. And if you look at it, we've got this value in the range, which is not being mapped by any value from x. It's allowed on a one-to-one function. We can have some of the values in the range not being mapped by this value. It's allowed, but you are going to see that on some of the relations, it's not going to be allowed. So that's a one-to-one or an injective function. And we are saying at most one. Whenever you have this one pointing to B and this two pointing to B, it's no longer a one-to-one relation. It's no longer a one-to-one function. Take note of that. We are saying there is at most one x. It's an element of x with f of x is equal to 1. So we do not want to see a 1 mapped to B and a 2 maybe mapped to B. It's acceptable. That's when it's a function, but it's not acceptable to be an injective function or a one-to-one function. Because we are saying we only need to have one of these mapped to one of these. Just like that. Then the graph, try to get someone. Then the graph of a one-to-one function or an injective function. This one, it's a what? It's a one-to-one function. Why? If you look at this one, this is the graph, right? So if you look for every value of x, we have got a different value. For every value of x, we've got a what? A different value, a single value, something like that. So this one is mapped to only this value. But this one, it's not a one-to-one function because on -2, we are going to have a 4. On the +2, we are going to have a 4. So we end up having -2 and a 2 pointing to one value on the y side, which means it will be wrong for a one-to-one function. We only want one value to point to a corresponding one value, not two values pointing to the same value. It's not a one-to-one function. Let's talk about the surjective or an onto function. Whenever you're asked of an onto function, onto like this, or know that you are being asked for what? For a surjective function. So by definition, if f is a function from x to y and the range of f is y, f is said to be onto y or an onto function or a surjective function. So the function from x to y is onto each element, or when each element in y in its arrow diagram, we have at least one arrow pointing to it. So now we are looking at this side of the range. We must have at least one arrow, which means it is allowed to have more than one, but every element must have at least one. So in other words, this one is not a surjective function because this D have got no arrow pointing to it. So here we are saying on injective, this shape is not allowed where you have two elements here pointing to one, because it's only at most one pointing to one here. But here, that shape is allowed, but only that every element here must have at least one arrow pointing to it. So you can have more than two arrows pointing to A like these two, but here it's not possible, because whenever you have two pointing to A here, it's no longer in a function, because two pointing to A while two pointing to C is now not a function, because it's like one to many values. So it's not a what, it's not a function. But only a surjective, we are just looking at this. Whenever you have any element in the range not being mapped by any value from the domain, it means that function is not a surjective function. I don't know, do I have some questions on injective and surjective? Can you differentiate these two? Just want to hear from the floor. Do I have some questions here, or do I need to clarify more?
Sorry, sir. I think you may need to clarify more, but first I need to test myself if I got what you're saying. On subjective, you're saying if we're having like a one pointing to A that is horizontal, we are having subjective, at least one. So if we are having two pointing to B, it's still subjective.
If we have a 2 pointing to B, it's no longer a function. If 2 points to B while 2 is pointing to C at the same time, it's no longer a function. Remember, you need to check, is it a function first? So it's no longer a function, so it cannot be a surjective function.
No, I'm saying 2. Okay, we can remove it from 2 to B to C. Then we point at B. I mean, okay, let's give an example for, I wanted to get two horizontal horizontal lines.
So you want to have something like this, maybe 1, 2, 3, and maybe here we've got a 4, maybe we've got a 6, maybe we've got an 8. All right, maybe we have another one, maybe as maybe 2. So you want to have something like this, maybe these two pointing here, maybe pointing to 6, and maybe having this one pointing to here, and then this one pointing to here. And want to ask, is this is still a surjective function?
Yeah.
Okay. And okay, and you wanted something. What else? What else? What else can we do? Okay. But I think your question, or the question that you're asking, I don't think if I made it. I'm sure you wanted two arrows at one.
Yes, I wanted two arrows, like let's say.
Okay. Maybe I can have maybe a 10. Maybe this 10 pointing to this 2.
Yeah, it's horizontal now, it's equal. Then I'm saying, is it a subject? Because it's at least, you're saying it's at least 2.
Yes.
Yes.
You are saying at least 1. Okay, it's a surjective. Yeah, it's surjective. It's a surjective function because we are saying at least 1. Okay, we must have at least one arrow pointing to those elements in the range side or in the Y. So if you look at this one, here there's an arrow, which means it's at least 1. Here there's an arrow, here there's an arrow, here there's an arrow and another arrow, which means it's still at least 1. What we just want is for it not to violate the rules for it to be a function. So once it is not violate that, so this one is a surjective function. Are you answered?
Yeah, I'm
okay.
answered.
Okay, so let me just move on to the graph of an onto or of a surjective function. This one is an onto function. If we look at it, we are saying we can have at least one value for every value. It's acceptable to have at least one value. Like here on this one, if you touch an X, you can get a value, can get a value on the Y. And then this one, we are saying this one is not an onto function. If you look at this, why is it not an onto function? this one, let me try maybe to touch on these values. This value is different from this value, but pointing to the same value, but that one is not supposed to be a problem. Why this graph is not, let's certify why this graph is not an onto from this definition. We are saying here you can have at least one arrow pointing to this one, which means it's acceptable to have different values, maybe pointing to the same value. But why? Why this one is not an onto? Because I'm not seeing it. I'm not seeing it. So I'm suggesting maybe it's a wrong diagram, but I'm trying to analyze it. Where is the problem with this one? Where is the problem? I'm alone now. Am I alone? Okay, I'll ask you to go and verify on this diagram. To go and verify on this one. For the sake of time, let's look on the bijective or one-to-one correspondence. You equate one-to-one correspondence or just bijective. So we have got the injective, the surjective, and bijective. Bijective, by from two. By means two. So a function that is both one-to-one and onto is called a bijective function. So something which is surjective as well as injective is the one which is a bijective function. So you just need to know the injective side and then the surjective side. Once you know that, you can tell this one. You can tell if it is a what? If it is a bijective, so or not. So the function f, which x mapped to what? To y, defined by the arrow diagram, is both one-to-one and onto, hence a bijective function. Let's look at this one. Can we say this one is a one-to-one or is an injective function? Yes, we can say so. Why? Why can we say so? If you look at this, one of these are pointing to one of what? To one of the values in the range. So at most one here. So we do not have an element which is not pointing, which is not pointing to the values in the range. And if you look at it, whenever we have an arrow from A, it's just a single arrow. So it's at most one arrow going to one of these in the range. So this one it's a what? It's a one-to-one function, or it's an injective function. What about a surjective? A surjective requires this one to have at least one arrow. So on every value in the y, we have got at least one arrow. So it means this one satisfies the onto as well as the one-to-one. So it's a bijective function. So it's both injective as well as surjective. So it's a bijective function. So the graph of a bijective just look like this graph that we have. There's someone who want to join. You can just go on to look on these graphs. Why are they? And then before inverse function, maybe I want to take some questions on the bijective function. Maybe we can unmask some of the things. Do we have questions on the bijective function? So maybe we can unmask some of the things. We can assume that if you know the injective and surjective, you can know the bijective, because you want to just cross-check if it is both. Once it is both, yes, you can just certify it is a bijective function. But do I have some questions on this one? Do I have some questions on the bijective? Okay, what about the contributions? Or some are not the questions, so but are some but are contributions. Okay. I'm sure people are now tired. They do not want to participate, but anyway, it's fine. Let me go on to the inverse of a function, just like the inverse of a relation. So it's the inverse of a function. So there isn't much that we can talk about here on the inverse of a function, and do not ask much, which is more than this. So let F be a one-to-one correspondence from the set, and a one-to-one correspondence is a bijective function. So from the set A to the set B, the inverse function of F is the function that assigns to an element B belong to B the unique element A in A such that F of A is now equal to what? Equal to B. So the inverse function of F is denoted by F to the power negative 1. Hence, the inverse of F at B is equal to A. So whenever you have the function F of B, the inverse of this function is now, whenever you put B, you get A. Here we're saying if you put A, you get B. But on the inverse side, whenever you have the inverse of this function, whenever you put B, you must get an A. So it's now vice versa, just like what we are doing on the relation. Remember, we've said a function is also a relation. So that inverse of a relation is just the same as the inverse of a function. So whenever you have an f of b, the inverse of that will be f of b must be equal to a. So the inverse of f, whenever you put b, you must get an a, just like that. So here, this is the diagram that we have for f of a. We are saying, let me try to interpret this. All right, from this side to this side, we are using the f of x or the f of a. Then going back, we will be using the inverse. So whenever you have this value, to find this value, we are using the inverse. From this one going to this, going forward, we are using the function itself. And then going the reverse side, we are using the inverse of that. So just like that. So from here to here, we are using f of a. Putting f of a, we are going to get b, right? So b will be equal to f of a. Then using the inverse, we are saying a will be now equal to the inverse of f at what? At b. Whenever you put b on the inverse, you are going to get an a, something like that. That's what we call the what? The inverse. So the inverse of a function, if you have this 1a, then 2a, and then 3c, the inverse of it will be this a pointing to 1 and 2, or whenever we have an a in our inverse, we are going to, as domain, we are going to get 1 and 2, and then this one is going to give us a 3. Just so this one will be the inverse of G. This one will be the inverse of G. And you have to know that not all the inverses are functions. You need to know that not all the inverses are functions. So here, this is that a contribution, or it was just a mistake? I think it's just a mistake. Okay, so I'm just saying here is just the reverse of this one. So you have A pointing to 1 and A pointing to 2, and then C pointing to what? Pointing to 3. And if you look at this, is this a function? You can safely say no, because this one is not pointed to any of the values in the range. So the inverse of a function doesn't mean that that inverse is also a function, unless we restrict some of the values in the domain. So inverse of a function may not be a what? May not be a function. Just like this one, it's not a function because this C is not pointing to n of, or it's not mapping to n of the values. So whenever you have a value in the domain which is not going to give you the value in the range, it means that one it's not a function because it's not producing the correct values at all. So just like that. So this was it, or this is it on the inverse of a function. I don't know inverse of a function. I think these are just the the examples. I don't know if there are some questions. I can take them before I move on to the next topic. No, not topic, is the next subtopic. Yeah, the subtopic. Okay. If I do not have questions or contribution, let me move on to this subtopic. I was just trying to rest myself. I talk too much. So maybe when you ask something and then others try to figure it out, then I get some time to relax. I do not have any water in here, so yeah. But anyway, let me try to push myself. Okay, so let's talk about the functions composition. Let's talk about the function compositions. So since functions are special kinds of relations, we can form the composition of two functions, right? We are saying since functions are special kinds of relations, we can also form the composition of two functions. Remember, we have actually managed to also form the compositions of relations. So we can also do it on what? On functions. So specifically, suppose that G is a function from X to Y and F is a function from Y to Z. The resulting function from X to Z is called the composition of F with G, and it is denoted by F of G. I think I've got some questions from other students were asking me to clarify this F O G and F dot G. This F O G and F dot G. I'm sure by the end of this lesson, you must not have a confusion of these two. So we are just saying, like what we were doing on the relations, we were saying if you are given a relation R1 and R2, where you have maybe the X and Y, maybe and the Z, right? This one is what? This one is another. These are, take them as just rectangles. So you have the values which will be mapping from X to Y and then from Y to Z. So you are saying whenever you have a certain value, let's say it's a 1 mapped to 2 and then 2 is mapped to 3. So it means that this value is also mapped to this value in what? In a set. That's the composition relation. We are saying by putting the value of Y here, we can get the value of Z, something like that. So that's the composition relation, and also that's the composition function. Taking the value of Y, put it into X, you can get the value of Z, something like that. Or if X and Y are related and Y and Z are related, it means also X is related to Z, or we can get the value of Z. X na Y kana dziri hama, Y na Z kana dziri hama, X inenge iri hama yani ya Z. You can always drive that relationship. That's the function composition. That's why whenever you say F of G, you take the value of G of Y semina F kutuane the value yani ya Z, something like that. That's what it is. So given G 1A, 2A, and 3C, a function from X 1, 2, 3 to Y, A, B, C, and F A, Y, B, X, C, Z, which is a function from Y to Z. The composition function from X to Z can be represented by an arrow diagram as follows. F of G, which will be 1Y, 2Y, 3Z. If you look at this, we've got X, Y, and Z, and then we've got this F of G. So we are saying here we've got 1A, this 1A, which is plotted here 1A, and we've got this 2A plotted here 2A, and we've got this 3C plotted here 3C. At the same time, we've got this relation from Y to Z, which we've got AY. This AY is plotted from A to Y, B to X, this one, and so as C to Z, which is C to Z. So whenever you want now X to Z, we are just saying if we put this A at this X, we are going to get the value of what? The value of Z, which is this Y, or the value of this side. So we can have 1 and Y, that's why we have this 1 and Y. You can have 2 and y, which is 2 and y through a, which is this value. You can also have 3 and z through this c, right? So normally I was just saying, if you put some of these values which are in here on the value or on this side, you are going to get these values which are here. Something like that. So that's the composition function. So maybe this is just by definition. Here we're using the pictorial representation. But now let's use the function composition or this notation, the alternative notation. So a composed function g of f is the function given by g of f of x. Not gonna be yakadai, so it's just as the same as writing this. Where you are saying for every value of x at g or at function g, just going to replace it with the value of f of x. So this sometimes called a function of a function, and the alternative notation of gf is g_o of or g of f. It's not a dot. If it is g dot f, it's a multiplication. So here it's just also the same thing that it is written as this one, or you can write it as this one. So take note of these notations. If you get g of f, then of x, you are just saying, take the value of f and put it in what? In g. G of f of x, you're just saying, when there was an x, go and replace it with the value of f of x, right? So this is, here I was trying to emphasize that the symbol for composition is a small circle. This one for function composition is a small circle. It is not a field in a dot like this one. This one is for multiplication. Whenever you get these dots, just multiply those two, the g of x and the f of x, just multiply those two. So before the set operations, maybe I would want to give an example here. There wasn't an example because I added this part. It wasn't there on your slides. So yeah, maybe you might want to ask me to share or to update the slides on your portal, because I might forget that. Okay, I just wanted to put an example. Let me just have maybe f of x. I'm just writing using a mouse, so it won't be clear. My PC is not a touch screen, so yeah, it's not easy to be accurate. Let me just have maybe x, maybe +1. Let me have a g of x. Maybe a g of x is maybe just want something simple. X +2. I just want you to see how you can solve this. And then you are being asked to find g of x. G of f of x. Sorry, g of f of x. So this one, what you'll be doing, you are taking the value of f of x and put it in g of x. So the value of g of x is x +2. So pana x up, you're just going to replace with the value of f of x, which is x +1. So pana x up trungono is an x +1. And then there is this +2. So at the end you get x +3. But if it was this one, you're just going to multiply these two. You're just going to multiply f of x and g of x. So I think this one must be clear. Do I have questions on this one before I move on to others? Do I have questions or contributions? Do I have questions or contributions? Or people have actually taken their break? Because it's now 8, so maybe people want to eat, and yeah. But anyway, because now people are too quiet.
Following, say.
Okay. Ian, Tendema, we can unmute yourself and contribute if you want to contribute. If you want to ask, you can ask. Ian, there was a hint by Ian, unless.
Say, can you give us an example of how you can multiply? Some of us are not familiar with this.
Okay. For the multiplication, we are just going to do an example on that one. It's on its own. Okay, I just mentioned it when I was doing the function composition, just because it confused a lot of people, the composition and the multiplication. But otherwise, on the operations, here is the operations with the functions. You can do the addition, you can do the subtraction, the multiplication, as well as division. You just treat it the way you do when you are doing the algebra or the symbol addition, mathematics, subtraction, as well as multiplication and division. So let us try doing those operations on f of x and the g of x. You are having two functions, the f of x and the g of x, and then you want to do the addition operation. So if you are asked to do the addition, or if you are given something like this, f plus g of x, what you are supposed to do is just to add the two functions. For example, you've got f of x is 2x plus 3 and g of x is x squared. So it's f of x plus g of x. So it's just adding 2x plus 3 plus x squared. That's what you have. And you know what you have to do with algebraic expressions. I will not dive into this one. I'm sure at all level it was there. You just add the like terms. So x squared plus 2x plus 3. That's your result. So that's how you do add two functions. That's how you add two functions. That's how you add two functions. I'm sure it's very clear here. Then on the subtraction, this is the notation. Normally you can be given it as this one, f minus g of x, f minus g at x, or just given f at x minus g at x. So this was just the same. It's just the same. So if you're being to subtract f of x, g of x from f of x, here you are given 2x plus 3 and x squared. So what you just need is just to subtract 2x plus 3 minus x squared. And then you know what to do. You subtract the like terms, and what you always get here, maybe it's just 2x plus 3 minus x squared, or just minus x squared plus 2x plus 3. It's just the same. That's what you get there. And then on the multiplication, you just multiply those two functions, and this is the notation for multiplication. So f of x times g of x, though this dot is for multiplication. So what you just do is 2x plus 3 times x squared, and you know the multiplication. X squared times 2x squared is 2x squared, then x squared times this 3, you're going to get 3x squared. So this one is x cubed. 2x times x squared is 2x cubed, and then this one is 3x plus 3x is x squared. I'm sure you know from algebra, you know how to expand these two brackets. I'm sure you know, or multiplying by a scalar. I'm sure you know what to do there. On the division, it's just the simple division. F of x divided by g of x. Just f of x divided by g of x. Each palm storage in the denominator are going. So it will be 2x plus 3 divided by x squared. If there are some of the things that you can do, maybe factorizing and then cancelling those that can be cancelled, you can just do that. I'm sure normally you need to leave this one in its simplest terms, but for this one, that's its simplest terms. I don't know if I've got some questions on functions. Do I have questions on functions or contributions? That's the time to do that. Do I have questions, contributions? Okay, so if I do not have questions or contributions, maybe the next topic was on, okay, there's a hand by Ian. Yes, you can contribute or I can ask.
Say, I wanted to ask, is it possible that you get a question where it says find the domain of the function?
Yeah, maybe you can be asked that to find the domain of a function. Is it that hard to find the domain of a function? The possible, both the domains just the possible values of x,
Okay,
and
yeah,
then
thank you, sir.
okay, and then the range is just the possible values of y. So I'm sure if you do more examples of functions, you understand it and you get it, and it is very simple. You find out sometimes the domain, maybe it will be maybe the values, maybe the positive integers or the negative integers or whatever. You just look at the values that can be taken by that function and then the output, then you can just give your answer there. I'm sure it's very easy. You can watch some tutorials there, but I'm sure
Okay,
most
thank you, sir.
the things which are very important are the ones that I've covered in this tutorial. What about others? Okay, so if I do not have questions, I wanted to do the sequences, but let's do them on the next tutorial. We will be doing propositional logic and maybe the logic gates, and then we close the chapter for mathematical foundation. So I look forward maybe to the next lecture on maybe on next month. So if we do not have questions or contributions, we can call it a day, unless if there are some questions, but I am sure I can call it a day. And have a good night.
Thanks so much, sir.
You're welcome.
Thank you, sir.
Thank you so much, sir. You really helped us a lot.
Thank you.
But it was a challenge.
I will share the recording.